Thanks very much for the invitation. So today I'm going to speak about the second half of my PhD thesis, and this will concern reduction of a certain type of representation of the local absolute Galois group. So I'm going to start. Yeah, so I'm just setting up the notation. So for me, P will be an odd prime, and I fix for the rest of the talk by E finite extension of QP, and K will be a positive integer, and AP an element in the maximal ideal of the ring of integers of E. And so first of all, I want to define a two-dimensional E vector space. And so I will call E1, E2 a basis of it. And I define it as a filtered phi module. So this means that I define on it an action of Frobenius element that is given by the matrix or by the system that I put it below. And I fix a filtration. Now this object, this linear algebra object, thanks to a work of Colmetz and Fontaine around 2000, they were able to prove that there is a one-to-one correspondence to irreducible two-dimensional crystalline representation of the Galois group of QP that have fixed dodge state weights 0 and k minus 1, and such that the decrease of the dual is exactly this filtered module. So the important point was that if one wants to study, this family of crystalline representation, they are very important. They play an important role in modularity lifting theorems, for example. And just to give another example, if we take if we fix a level away from the prime P and we take normalized cuspidal eigenform of level n, then if P does not divide the level and this mild condition over the P coefficient of F is satisfied, then we have the restriction of the classical Deligne-Shimura representation that I can attach to F. If I restrict it to the decomposition group of P, then this is always crystalline. And it can be described exactly by two parameters, and this will be the weight of our cuspidal eigenform and the P coefficient. So the important result of Colmetz and Fontaine says that this class of representation depends essentially on two parameters. And this is something special that it works only for Galois group of QP. And I can describe them using a very simple linear algebra object. So what is our goal? Our goal is to classify in general this representation VKAP. So we know that when AP has positive valuation, positive p-adic valuation, these are representation are always irreducible. But as of now, that I know, there is not complete classification of this type of representations. And so instead of going directly to classify them, one can ask what are the relation when I let these two p-adic parameters vary, and how these representations are related. And the idea is exactly to check how p-adically close these representations are. So because of this, I want to define just like some notation. So let's fix two representation, two E linear representation of GQP, and we will say that they are congruent modulo a certain prime power if there exists a lattice in one and a lattice in the other representation that are both Galois stable, and such that they are isomorphic modulo prime power. So this means that they are isomorphic as Galois module when I take the quotient modulo P to the n. Now, of course, this is very far to be an equivalence relation, and so one has to be a bit careful when to use this thing, but it will be useful. And just by set another notation, so we define by V bar the semi-simple residual reduction of any GQP stable lattice inside the representation V. Now we know by Brouwer-Nesbit theorem that this does not depend on the lattice that we choose. And so in general, when we deal with the residual representation, because of fact that we can consider the semi-simplification, we don't have to bother too much about the lattice that we are considering or that we are using for the reduction. But if one wants to work modulo prime powers, then things might depend very strongly on the lattice that we choose. So this is something that we have to be careful. So in 2012, Laurent Berger proved that if we think of a map from that associate, so we fix, for example, first the weight, and we let the AP, the trace of this Frobenius element, vary periodically. Then we know that all these representations share the same semi-simple residual reduction. And if the thing is, it works also if we fix the AP and we let the weight vary under some condition. And these were the two results that Berger proved. And the idea is to try to generalize this this result modulo prime powers. And there are two techniques that I managed to use to study this type of problem. So I'm going to describe quickly. So the first result concerned the situation when we fix the weight and we let the AP vary in a small periodic ball. So what we do is we fix, so now I'm considering AP and K fixed, and also the integer M. No, it's not an integer because we allow some denominator, but it's okay. So what we do is we fix another AP prime that is sufficiently close to periodically close to AP, and then we are able to prove that the two representation VKAP and VKA prime P are congruent modulo P to the M. In particular, we are able to prove something a bit more, that is, for any GQP stable lattice that we fix in the representation VKAP, then there exists a lattice in the second representation such that these lattices are congruent modulo P to the M, modulo prime powers. So we can always find lattices that are congruent modulo prime powers under this condition. And I also want to notice that the radius that that we find for our local constancy result is explicit. This function alpha is a function in the weight, but it is very explicit and it can be computed. And the radius is also linear in the power of the congruence that we are interested in, that is with this M. So what is the main ingredient that of the proof is the following. So the idea is so let's denote by AE this ring. So this is the P. So by pi E I mean a choice of a uniformizer for the ring of integers of E, and we take the periodic completion of this power series rings when we invert the X as well. Now this ring is the one used by Fontaine to establish an exact equivalence between categories. So we have the category of OE linear representation of GQP. By this I mean not necessarily free, so they don't have to be lattices in some rational representation. I just mean finite OE modules with an extra linear action of GQP, and what are called phi gamma et al. Phi gamma modules. These are simply finite modules over AE, over this ring, with an extra semi-linear action of phi and gamma. Now gamma is a profinite, no, it is not profinite, yeah, it's a procyclic group under the assumption that P is not 2. And phi is just Frobenius endomorphism, as we saw at the beginning. The important thing is that we can describe, so this result allows us to describe an object that is relatively difficult to describe, that is a Galois representation, with an object in linear algebra. So this is just some finite module over AE, and we have an extra action. Since gamma is procyclic, essentially what we have is we have that the action of phi and gamma are respectively described by matrices. And so for phi, I will have one matrix that I will denote by G, or by, yeah, no, sorry, by P. And gamma, well, we choose a topological generator, and we take the matrix through which it acts on this phi gamma module, and this will be represented by a matrix, another matrix. So now if we restrict our attention to the OE modules with an extraction of GQP that are lattice inside crystalline representation, then Vac and Berger proved that the structure indeed of the attached phi gamma et al. Module is described exactly by these two matrices. And moreover, these two matrices has not coefficients in AE, as one could expect, but in actually power series only in X. So this makes computations very, very simple. And the idea is that this is especially helpful if one wants to deal with congruences between lattices, because now two lattices will be congruent modulo P to the M if and only if the two couples of matrices are congruent modulo P to the M. But this now I mean exactly as a p-adic numbers essentially. Well, p-adic power series, but that's essentially the same. So by this notation, I mean that P has to be congruent to P prime and G has to be congruent to G prime. And so using this theory, then the idea is just to prove that if we start with we start with a lattice inside the first representation, and we consider its attached system of matrices that we have. And the idea is to use some formulas to deform this couple of matrices p-adically into another couple of matrices that will represent another phi gamma, or well, another Vac module in this case. And this will correspond to another lattice in another crystalline representation. And now by checking numbers, essentially, you find out that you can keep the weight fixed and you can move the AP into another AP prime that will be sufficiently p-adically close. Now, of course, one has to pay attention because this matrices has to satisfy some relations. For example, the action on phi and gamma on the phi gamma module, this is commutative in a semi-linear sense, so that there is like some relation that has to be satisfied. But yeah, this is the main idea. The idea is just to deform Vac modules. This is essentially I think one of the beginning steps in the integral p-adic theory. One wants to describe some lattice inside crystalline representation via some linear algebra objects. And so that's it for the first result. And now for the second result, I want to focus a bit because the technique is rather different, but still interesting. So let's assume now, well, same assumption essentially. Suppose only that the weight is sufficiently high. What we are able to prove is that, so what we are doing now is fixing AP and let K vary p-adically. So what we are able to prove is that there exists an integer R that will depend on K and AP, such that if I take another K prime that is sufficiently p-adically close to K in the sense of closing the weight space, then the two representation VKAP and VK prime AP, they will be congruent modulo prime powers. So this means that there exists a lattice in the first one and a lattice in the second one, such that their reduction modulo prime powers is isomorphic as Galois module. Now, contrary to the first situation, I was not able to describe this local constancy radius explicitly. But there are some results using local Langlands methods. But so the problem here was that it's not possible to use the Vac module strategy that I've described before, and one has to rely on a bit more geometric approach. So the idea is that if the weight is sufficiently higher than the valuation of AP, then this crystalline representation can be described explicitly as what is called trianguline representation. So trianguline representation is a much larger class than crystalline representation. And essentially, it means that in the theory of Fontaine, if we take a representation of GQP, then this means that to be trianguline, it means essentially that the corresponding phi gamma module that I can attach, this linear algebra object, then it fits in a short exact sequence. Now I'm speaking about two-dimensional representation. So it fits into an exact sequence. So this means that it can be in some sense decomposed. And the idea is that this trianguline representation, they are parameterized as points in a rigid analytic space and defined over QP. So what we can do is that we can see these two representation VKAP and VK prime AP as points on this rigid analytic space that I called S. And the idea now is to create an analytic family of representations that essentially, so will depend on one parameter only that will play the role of the weight K, and it will join these 2 points. So the 2 steps that we want to do is, so the first part, as I said, is we can show that if we can join these 2 points by a p-adic family and we can control the parameter, then the idea is that if the parameter will be smaller p-adically, then the 2 points will be closer in some natural sense on this rigid analytic space. This means that there will be a sufficiently small open admissible open set that will contain both. And this essentially can be done through formulas directly. One just has to pay a bit of attention to the explicit description of these 2 representations as trianguline representations, but they are particularly nice to be described. So one just to find the right formulas. And the idea is that so we create this rigid analytic map phi to essentially a 1 p-adic interval to, well, here there is a bit of a typo. It's not x squared, but this S. So S is usually the notation for the Colmet's rigid analytic space of trianguline representations. And so we join them by a 1 p-adic parameter family. And then the second step is to use a result of Colmet's. That is that if we take a sufficiently nice point on this space, there exists always a sufficiently small open, admissible open, such that every point in this open corresponds to a trianguline representation, but they all vary in an analytic way. So in mathematical terms, a bit more precise. So there exists, so for any U that is a sufficiently nice point on S, there exists an admissible open. And if we denote by OU the functions that are defined on U, so let's assume that U is an affinoid space, just like sufficiently small to be affinoid, then OU will be an affinoid algebra. This means like some converging power series ring. And then there exists a finite and free OU module that we call V, that is stable under the action of the Galois group of QP, such that as every time that I specialize this module, this means like I take the quotient from the corresponding maximal ideal, the maximal ideal that corresponds to the point that I'm considering, I get exactly the trianguline representation that I was expecting to get. So it works well with specialization. And the fact that it exists, this finite and free module, it means that these representations in this admissible open, they all vary in an analytic way. And we can use this by essentially saying that, okay, then like I join my 2 points, UK and UK prime, that corresponds to the representation VK AP and VK prime AP. And I reduce the parameter. I will take it smaller and smaller until both of these 2 points are contained in the open, admissible open that whose existence is granted by the work of Colmetz and Chenevier. This means now that we have they are both like specialization of a rigid analytic family of Galois representations. And so what we can do is now just a last part, last algebraic part, essentially, that says that we are able to prove that there exists inside this rational rigid analytic space, since we are interested in integral representations, we are able to prove that there exists an integral subfamily that is analytic in some sense, that joins the two. So this means that then after specialization, we are able to prove that there exists a lattice in the first representation and a lattice in the second representation that have to be congruent modulo prime powers. And I can control the exponent of my congruence essentially by taking the difference between k and k prime to be bigger and bigger, or like maybe it's better to say smaller periodically. That's what I meant. So the closer these 2 points will be, the more congruent the two lattices will be, as expected in some sense. And yeah, so the subtle part in all of this is to actually prove that whenever we take our rational rigid analytic family of Galois representation, there exists an integral subfamily. So that this means that I can take a lattice in every single specialization, and all this one will behave accordingly in an analytic way. So this means that they will vary continuously whenever I the parameter that I decided to take. So things can get very explicit here. I was pushing to make things explicit in order to try to find an explicit radius, but the problem is the existence of this admissible open. In the work of Colmet and Chenevier, this is not done explicitly, even though these points can be described by like 5 or 6 parameters. I was not able to find an explicit description for which, like for every point, how big it has to be U to have the requested congruence. So that is where it fails the search for an explicit bound for the radius with this method, at least. And yeah, that's all I want to say about this. Thank you very much.